Okay, SHM graphs. How much? Okay. Yeah. Okay. Right, let's push on. We want to find a solution for x which satisfies our simple harmonic motion equation. So far, it's been a little unsatisfying. We've said, look, the acceleration is equal to some constant proportionality times minus x. But we haven't given a function in terms of time for, well, what does x actually look like? What's the graph of simple harmonic motion? This equation is a differential equation because acceleration, for those who do A-level maths, you will know that acceleration is displacement twice differentiated with respect to time. Velocity is displacement over time, but then acceleration is velocity over time. The net result is that acceleration is grab displacement and then differentiated twice with respect to time. So the real equation you're trying to solve here for x is this horrible linear equation. I need a function of time, x to be a function of time, such that when I differentiate it twice, it equals itself, but negative. What function satisfies that? It is cosine, or indeed either of the trigonometric functions. So it can either be cosine or sine. Sine differentiated by t is cosine, differentiated again is minus cosine, minus sine. Fab. Great, and this is why the use of omega squared is also mathematically useful, because it forms part of our solution. If we differentiate this function via the product rule, we have to bring out omega in front. Apologies if you don't do A-level maths. If you don't do A-level maths, you don't necessarily need to understand the differentiation aspect of this. You just need to understand, look, there's this equation that mathematicians can solve, and the answer is this, this, and this for the displacement, velocity, and acceleration. Okay. And if we plot this, we end up with amplitude here. You can see our period here. And all's well. And you can see, look, A actually is equal to the same thing as X, but it's negative and it's got this omega squared in front of it. So hooray, it does satisfy that differential equation. If I plot, then I've plotted X here. How then can I plot velocity? Well, I can consider the gradient. At t equals 0, what's the gradient of x? It is 0. Therefore, for velocity, it must start at 0. At this point, the velocity, the gradient of x is maximum. It says it's steepest and it's negative. Therefore, at this point in time on my graph of v must be at its lowest point, and so on and so forth. And you can just by looking at the gradient of this graph, you can plot this graph and then repeat the same trick with v. I can see at this point, for example, I can say, look, I can see that the gradient is 0. So if I find this point on my x-axis for the acceleration graph, lo and behold, I can see, look, yes, it really is 0, because each of these is the gradient of its predecessor. We plot a graph, and then we plot a graph of the gradient of our first graph. Right. The x max equals a, and that is at t equals 0 or one period or a whole number of periods. And I could rewrite that as n over f. Yeah. But I also know that omega is 2 pi f. So I could also write that as t equals 0 or some integer times 2 pi over the angular frequency. 2 pi n over omega. That's when we'll have maximum displacement. And it will repeat forever and ever and ever. Okay, what about our maximum velocity? When do we get our fastest motion? And what is the value? Well, the value, just looking at this mathematical function, sine and cosine, these two trigonometric functions, they always take values between -1 and 1. They can't ever be greater in magnitude than 1. So they're not super extreme. So what's the maximum value? Well, the maximum value of this that it can be is 1. So the maximum value of v that can take in terms of magnitude is a times omega. And that's going to be whenever x is 0. Because whenever x passes through the equilibrium point, that's when its gradient is steepest. Therefore, that's when the max velocity is. Okay. What about a? When's the maximum acceleration? And what's its value? Its value, using a similar trick, the maximum value that cosine as a function can take is 1. So the maximum magnitude of acceleration is a omega squared. And this always occurs when the maximum positive acceleration occurs when x is at its maximum negative displacement, and vice versa. So it occurs when x is equal to -a. I'll say plus or minus a, as long as you reverse the sign. So when x is at -a, the acceleration will be at its positive maximum. When x is at its highest point, the acceleration will be at its negative maximum magnitude. Okay. Does that stand to reason? Think about your girl on the swing. When x is at its positive maximum, so the girl is, or the boy or whatever, is swinging at when x is a max, so it's at fully forwards. What is the acceleration doing? It's at its maximum value pointing backwards. That is what happens. And when the swing is at the displacement is at its maximum negative displacement, what's the acceleration doing? It's at its maximum value, but it's pointing forwards. Okay, so that does square with our graphs. The displacement and the acceleration are always pointing opposite directions, which is a good thing because that is exactly that's what this equation up here is saying. It is saying, look, they're always going to be pointing in opposite directions. Okay, for a simple harmonic mass spring system, we can write equations for the energy of the system. Again, we won't worry with the derivation for this equation, but the energy of a spring is ½ kx squared. And that is that's elastic potential energy stored in spring. Okay, so when the spring is maximally extended, all the energy is stored as elastic potential. So when we're at extremes of x, the elastic potential, this green line, is at a maximum. Hooray! So here's minus A, here's plus A. However, in between, you get, where does the energy go? Obviously it dips, it's converted into kinetic energy. If I boldly attempt to draw kinetic energy, ooh, that's not such a good parabola. That's arguably a slightly better one. The kinetic energy, as I hope we all know, is half v squared. And the total then is half kx squared plus half v squared. And it's a constant. This faint red line up here is the total energy. Fab. It's a closed system, so we can't create or destroy energy. And I've jumped ahead of myself. I should have looked on the next page of the notes. But just as I said on the previous slides, the kinetic energy is always going to be, the total energy will be, well, it takes the maximum value here. I said this was minus A, and this was A. What value does the potential energy have here? It's half K A squared at its maximum. Therefore, that is going to be mathematically, these are all constants, half K and A are all constants. That is going to be our numerical value for the total energy. And you subtract from that half kx squared. And there's an alternate expression for your kinetic energy. If you then set it equal, to this, you can work out an expression for V. The halves cancel. You will need to square root, but you get half K over M A squared minus X squared. And if you are wondering, but we can then say, look, from a few slides ago, we know that omega squared is equal to K over M. Or rather, I think it actually said that omega is the square root of K over M, but hopefully you can recognize those are the same thing. If this is omega squared here, we can take that out. We can say, look, V is plus or minus omega times the square root of A squared minus X. What does that look like as a function? It looks like that blue line. If you get Wolfram alpha out or whatever and plot that function, you'll get an inverted parabola with a maximum value of omega A squared.